Chapter 4, Part 1, Working with the Normal Curve. The normal curve, or the normal distribution, is a histogram or frequency distribution that is unimodal, symmetrical, and bell-shaped. Sometimes we call the normal curve the bell curve. Researchers compare the distributions of their variables to see if they approximately follow the normal curve. It makes it easier to understand our population. And so in this chapter, we're going to be talking about our normal curve, and then later on we'll be talking about our population, samples, and probabilities. In this video, I'll just be focused on the normal curve and using the tables that were given for our homework and for quizzes so that you can better understand how to calculate the percentages using that table. Okay, let's get started. So the percentages under the normal curve, if you look at the entire normal curve, it is 100%, right? So 100% of the normal curve exists under the normal curve. So we have right in here, we have our normal curve, and you can see that the mean is right here at the middle. It's where the z-score is 0. And then we have one standard deviation below, and one standard deviation above is where the z-score is -1 and 1. And then z-scores of -2 and +2 are 2 standard deviations away from the mean. And then -3 and +3 are 3 standard deviations away from the mean. Now, if you look at the percentages underneath, if you look just at the mean and going all the way to the end, we have 2, 14, and 34%. This altogether is 50%. All the way out here is another 50%. And so understanding the percentages in the normal curve will help us to understand how many people are in our population when we're talking about comparisons. Okay, so let's look at how this works. So let's talk about a sample calculation. If Luke has a z-score of +2 or a +2 z-score on a language test, how many students did he perform better than? Okay, so here we have our mean, which is right here in the middle, and I've put this red line on the middle, and this gives us our 50% line. 2 + 14 + 34 equals 50%. Now we're going to get to Luke's score at the z-score of 2, we're going to add 34 and 14. So we can add all these percentages up and we get 98%. Or we can go the reverse and we can look at what's in the tail. In other words, who did better than Luke? And we can see that 2% did better than Luke. So if everything is 100% and 2% did better than Luke, 100 minus 2 equals 98%. Okay, so let's think about that as we go through. We're going to look at different variations of calculations using the normal curve. Now, as we go through this, you need to remember the formulas that we've used before. To find a score, when you know the z-score, the mean, and the standard deviation, you will use the x equals z times standard deviation plus the mean, and x is the score. When you need to find the z-score, and you know the score, the mean, and the standard deviation, then you use the formula z equals the score minus the mean divided by the standard deviation. So you'll be using these back and forth throughout this chapter. Okay, so example number 1, we're going to be looking at IQ scores. If a person has an IQ of 125, what percentage of people have higher IQs? Well, one of the things we know about this IQ test is that the mean is 100. So we see that 100 is right here in the middle with the z-score of 0. We know that the standard deviation is 16. So that a z-score of 1 is 116 and a z-score of -1 is 16 less than 100, which is 84. But our person has a score of 125. So that's kind of in here between 1 and 2. So we're going to calculate our z-score, using our formula, so we get 1.56. We're also going to draw a picture of the normal curve with the estimation of our answer, okay? And you're going to shade in where your answer should be, okay? So when you're doing your assignments, you need to draw the actual normal curve. You'll get good at this. I just draw it, and I draw the mean, I draw the line going across, and I estimate about where my z-score is. And then I want to shade in this part because I'm looking for people with higher IQs, okay? Okay. Now the next part, I need to look up this z-score that we calculated, 1.56. I need to look it up in the table. Now this table, if you have the physical book, it is in the back of the book, in the appendix, okay? But it's also in our ebook, in the appendix, Appendix A, and you can look it up there. And in our homework assignments, they give you access to those tables, and they summarize them for you, or they'll give you the pieces that you need. But and so I'm showing them to you here on the screen, but they are given to you in the book. You can also Google them to find them in other places. But when I did that, I found that they didn't have these nice graphics at the top of the chart, which help you to understand where you're looking, okay? And that makes a difference on how, which part of the table you're going to find your answer. Okay, so we look up our z-score in the table and we find 1.56. I've highlighted it for you. And we see two pieces of information. We see the percent of the mean to the z, that's under here. So we see this first part, and we're picturing our normal curve, and we see the percent from the mean to our z-score of 1.56 is 44.06. And we see the percent that is in the tail, 5.94. So, which one is our answer? Think about that for a second. We want to know what percentage of people have higher IQs. So as you're thinking about that, I want to show you a trick. We have two answers, but since we are looking for the people with the higher IQs, we want the percent that is in the tail, okay? So this part right here is called the tail of the normal curve, and we want the higher IQ. So here we have our answer, 5.94% of people who have taken this IQ test, and there have been, you know, probably hundreds of thousands, if not millions of people who've taken IQ tests. So if you have an IQ of 125, then only 5.94% of the population has an IQ higher than you, okay? And you can check that your exact percentage is within the range of your rough estimate. And you estimated that it would be between a z-score of 1 and 2, and you estimated that it would be right in here. We also know that it would be less than 14, more than 2% because of where it is on the normal curve. Okay? I also wanted to show you that since we are looking for it in the tail, you can also see that our graphic here at the top of the table also gives you a clue about which part of the table is the best place to find your answer. Okay? They match. All right, let's look at another example. If a person has an IQ of 90, what percentage of people have higher IQs? Well, now we are looking at a much larger piece of the normal curve. It's not just this piece up here that's part of the tail. In fact, it almost looks like we have the tail that is missing from our answer, and we have this space between the mean and the z-score plus this 50%. So let's look at it. We've calculated the z-score, so we've plugged our numbers in. The score is 90 minus 100 divided by 16, and we get a z-score of negative 0.63. So between between 0 and negative 1 is our z-score. We draw a picture, with an estimation of our answer, okay? So this is a larger amount. We can automatically assume that it is going to be 50% plus whatever is here. So we need to look it up in our table. So here we have our table again, and I've shown you just a brief part of it. We looked up 0.63, but you'll notice that our table doesn't tell you positive or negative. In fact, it only gives you the positive numbers. Because the normal curve is symmetrical, it is going to be the same size, whether it's on the positive or the negative side, and so you're just going to imagine it, the mirror image of it, on the other side. So this 23.57 part is what's between the mean and our score, and the 26.43 part is what's in the tail, okay? And since we're talking about this part plus this 50%, then we have the 23.57% plus 50%, or 73.57% of people have a higher IQ than 90 on this IQ test. Does that make sense? So since the z-score is negative, we want the amount between the score and the mean plus the 50%. So our answer is 73.57%. Okay. Now let's talk about how we might do other examples. We were using the score and having to change it to a z-score. Now let's just look at it with just a z-score. Another test. A researcher is looking at test anxiety using a particular measure she administers to students prior to midterm exams. On this measure, she has found that the distribution follows a normal curve. Using a normal curve table, what percentage of students have z-scores below 1.5, above 1.5, below negative 1.5, and above negative 1.5? So I've given you our normal curve, and I have marked the 1.5 for negative 1.5 and positive 1.5. I've also highlighted the part on our chart, on our table, excuse me, of the 1.5. So we have the percent mean to z and the percent in the tail. And each one of these is going to give us a different kind of answer. Let's look at each one in turn. For below 1.5, we have a very large group. So if we are looking at the percentage of students who have z-scores below 1.5, this is a large group of people. We look on our chart and we see the mean to the z-score, right here is 43.32, and then we also add the 50. So 93.32% of the students scored below a z-score of 1.5. Okay? What about above 1.5? Notice that above 1.5 is in the tail. So we're going to look at this number over here. That number is 6.68. Simple. 6.68% of our students scored above a z-score of 1.5. What about below 1.5? Again, it's in the tail. And even though it's negative, it's still on the other side. It's symmetrical, so it's the same amount. It's in the tail, so it's 6.68%, not negative 6.68%. You can't have negative percents of students. In this case, we're talking about the same number of students, but we have the same number of students are above 1.5 and the same number of students are below 1.5, negative 1.5, excuse me. Now what about above negative 1.5? Do you see a pattern here? Let's see what happens. Above negative 1.5 is going to be the same as below 1.5. It's symmetrical. It balances out so that the percentage of students who scored above negative 1.5 will be 50 plus 43.32, or 93.32%. Okay, Here's another example. This researcher who was looking at test anxiety is using that particular measure, so we're looking at the same measure. We want to know what is the lowest score on the test anxiety measure a person has to be in the top 40%, the top 30%, or the top 20%. Now for this example, we want to find the lowest possible z-score for the percentage range and then convert that to a score, because we want to see what score a person would need to get on this measure to be in the top 40, the top 30, and the top 20%. So let's look at how we would do this. Since we were looking for the lowest score in a range at the top of a curve, we are looking for the percent in the tail. For the find the percent number in the percent in the tail column and locate the z-score for that percent in the tail, okay? And then we're going to convert it to a score. So let's look at the table. So here we have a couple of them. We have 20, let's see, oh, here we go, 0.25 z-scores, but here we go. We're looking at, the percent in the tail is close to 40% right here. So here's 40% and here's 30%, and I don't have the table including 20%, but you can find it the same way. Now how do you know which one is which? You could estimate and go in between, but a z-score at the 2 decimal places is perfectly fine. What I do is I go to the one that is closest, and so for this one, 0.13 is closer to 40 than the, what would that be? 0.26 away from 40, so I will go with 0.25. Okay, and what I'm doing is I'm just looking at how far away these are from 40. Okay, so 0.25 for the 40, and then for 30 we have 29.81, that's 0.19 away from 30, and 30.15 is 15 away from 30, so we'll use the 0.52 z-score for the 30%. Notice we are still looking in the percent in tail column. Okay, so in our example, the values for the test anxiety measures are the mean is 15, the standard deviation is 5. So for 40%, the z-score was 0.25. For 30%, the z-score was 0.52. And I did find that the 20% z-score was 0.84. Okay, so I calculate the score using our formula. Here's our formula right here. Z times the standard deviation plus the mean. And that gives a score on this measure of test anxiety to be in the top 40% of students having test anxiety. They would need to score 16.25. Top 30%, 17.6. To be in the top 20%, a 19.2. Okay. And that, my friends, is how to use the table. Isn't that great? We did that in less than 20 minutes. Email me if you have any questions.